Hello everyone, my name is Cilk, and today we're talking about a simplified and extensible Cilk runtime for research. Now, let's begin with some background and motivation. So we all know what Cilk is. It's our extension to C, and it introduces two keywords, spawn and sync, which do about what you'd expect. Now, the most used runtime implementing Cilk is the Intel Cilk Plus runtime. In addition to implementing those core keywords, it also implements a number of other non-core features, reducers, pedigrees, support for multiple user threads, thread building blocks, interoperability, and exception handling. Now, let's say we want to modify the runtime. Maybe we want to implement experimental new features for the runtime, such as alternate implementations of pedigrees and reducers, modifying the underlying scheduling, such as by treating Cilk verbs as proper entities rather than function calls, or ensuring that when code is switched between the workers, acts don't suddenly fail because the thread line changed, or allowing instrumentation tools like CSI to differentiate between the runtime code and user code. Or maybe we're not doing any of that, and we're teaching a class like 6.1.7.2 and want to cover the runtime. As we'll see later, the algorithms behind Cilk aren't very complex, like the various algorithms behind the core Cilk features aren't complex. Moreover, Cilk Plus is a professional commercial product produced by Intel, so surely modifying the runtime should not be a monumental challenge, right? Wrong? The first issue is that Cilk Plus is just plain large, so let's start by looking at lines of code. According to slot count, if we run it on the runtime folder of the version of Cilk Plus included in GCC, we get 8,500 lines of code, the vast majority of which is regular C code. There's also another 1,000 or so lines in a safe strings subfolder, but we'll exclude that for this one here. Now, that doesn't sound too bad. However, it gets much worse when you include documentation. Namely, if we run CLC on that same runtime folder, we get more comments than there are lines of code. This, as you can see, includes that extra 1,000 lines in these safe strings subfolder. But hey, documentation isn't bad. That just means it's well documented, right? Wrong. Again. Even though Cilk Plus has so much documentation, it's not of the best quality. Let's look at an example here. Let's go back to reducers. Suppose that we need to see the protocol for implementing them. Where might that be? It should have its own dedicated page, right? No. Well, maybe it's in the header file for reducers. Again, no. Maybe it's in the source file for reducers. Yeah, still no. But what about this random line in the scheduler file? Yes, that's where it is. And on that note, if we aren't experimenting on reducers, do we even need them? Do we need to know how they work? They are one of those many non-core features on which a lot of code is spent. Moreover, as some Intel slides noted, for the most part, those features can usually be ignored when we're beginning experimentation. So we should be safe to just ignore this, right? Wrong. Again. So, for reducers in particular, we cannot ignore them because some core stack manipulations occur in the function finish spawn return on user stack. This is specifically having to do with fiber manipulation, which we'll get to later. And our sense can harmless until we realize that finish spawn return on user stack is called from the reducer function execute reductions%. Why? I don't really know. It's never mentioned. And the problems of this messiness extend beyond lack of modularity in the code. For example, there's a lot of dead code in Cilk. Oftentimes it's even simply wrapped in if-zero preprocessors or statements, and they're usually preceded by reassuring comments like this. This code was never encoded anyway. Well, is it safe or not to remove? Doesn't say. Or maybe to be done, the logic needs to be revisited. We have no idea if this is actually right. Again, you can see why this would be problematic. So, hopefully by now it should be pretty clear that we need a simple, hashable runtime. And any attempt is going to need to meet three primary criteria. First, it's got to perform comparably to a Cilk. Second is that it has to be short. We set an initial target of less than 5,000 lines of code. And third, it's got to be simple. We can't have that mixing of the different parts or the dead code. Now, our attempt at this was called Cilk, and it draws from two previous runtimes. First is obviously Cilk+. For all its problems, it is still a pretty good runtime. We can't just throw it out. But also we use Cilk, which was a very interesting runtime, which was known to be very simple, and it used a cool technique called thread over memory mapping, which we'll get to in a bit. Unfortunately, TLMM only runs on an old patched version of Linux. That's a kernel patch, so it no longer works. And in fact, no MIT computers can run it anymore. In fact, I'm pretty sure no computers, period, can run it anymore. But the source code is still there for us to use. Alright, so now let's look at what it takes to make a minimal runtime like Cilk. So, for all versions of Cilk, they implement a work stealing schedule, which divides work efficiently among various workers. Each worker in particular saves its state in a deck upon reaching a spawn. An idle worker will pick another worker and try to steal work, and this thief worker will attempt to transfer one of the suspended states from the victim worker to its own deck, and the thief will then resume execution of the stolen state. Now, as high level as that was, that didn't sound too hard. Sounded very simple. And indeed, there are really only two major areas that need particular care here. First is when we resume a state, we have to make sure not to clobber the victims execution step. And second is that when managing a worker's debt, we need to use a non-trivial bookkeeping. Let's start with that first point. In effect, what's happening is that a function in Cilk may have multiple cars running at the same time. It's something like the A part of this diagram, and what we need to do is make sure that each execution step simultaneously works like it does in the B diagram. A system like this is called a cactus step, and there are a couple of different ways we can implement this. Cilk uses something called fibers, which are very just large segments of virtual memory. We can, by setting the stack pointer to the base of the fiber, ensure that future execution continues on the new fiber. In contrast, Cilk uses that tool I mentioned called thread local memory mapping, which allows manipulation of the mapping from virtual to physical memory. That way we can have each thread seeing the same virtual space but operating on different values on different pages. Now, the second point about work steering is that there's a standard way of implementing it. This is the bookkeeping for the deck. In effect, each worker breaks its task stack into a bunch of smaller chunks, and these are divided by potential spawns. If the function might spawn something, then it is one of these chunks. And these are then grouped into stackers, which are divided by actual spawns. And these are stored in a spawn deck that looks something like this. So we have a head at the top where the car stack begins. Then we have the individual tiny chunks, specific stack frames in these stackers. And these can steer and resume execution of the top of a victim's spawn deck. Not to be confused with the tail, which is at the bottom, not the top. Now, Cilk itself implements these areas as follows. It uses the fiber-based implementation of cactus stacks from Cilk. As nice as the TLMM version is, as we mentioned, that really doesn't run anymore. However, it does use Cilk's implementation of work steering. There are some subtle differences between the two, even though they're following the standard algorithm. And over nights of coding this, we run into a number of stumbling blocks. For one is that the compiler greatly hampers manual management of the stack pointer. As we mentioned, Cilk's scheduler sadly varies from the standard steering algorithm. And Cilk's fibers completely lack the usage protocol. We had to entirely reverse engineer that. However, back in May, we did manage to get a semi-working version of Cilk, the error.error.min alpha. Now, we computed the furthest Fibonacci number for a standard Cilk test using serial implementation, Cilk on 2 workers, and Cilk on 2 workers. And that gave the following results. Serial was done in a third of a second. That was with O2 optimization on Fib, and obviously no optimization on the runtime. Cilk ran in about 3.5 seconds. That was with O2 optimization on fib, and an unknown runtime optimization, whatever their standard is, which we now think is O3, but we're not quite certain. And Cilk ran in 5.5 seconds with O2 optimization across the board. So, obviously that's not quite as good, but it is relatively comparable, and loss of inlining and compiler integration probably significantly harmed that performance. So overall, we're relatively happy with this result. So, now that Cilk meets our first criteria for a new runtime, let's look at the second. How long is it? So, if you recall, according to slot count, Cilk passes about 8,600 lines of code, 9,700 if you run count that safe string subfolder, and about 5,000 net standard C, and another 3,000 in C++. Cilk M is 9,200. Even though it's simple, it's still fairly long because of some features it includes. That's almost all in C, but there is some assembly in there. Cilk, in contrast, is under 2,000 lines of code, and that's all pure C. So naturally, we're very happy about this result. Which brings us to the third question. Is it simple? But we think so. More objectively, the code is a bit better organized. However, the documentation is incomplete. So, with that all in mind, it sounds awesome, doesn't it? It meets all criteria. It's comparable in performance, it's short, and it's simple. Or at least we think so. So that leads to a natural question. Can we use Cilk yet? No, we cannot. The issue is that Cilk has a figured bug involving fibers, specifically the following use case. So fiber 1 is executing code, and it reaches a spawn. It then continues executing the spawn code. Meanwhile, fiber 2 comes along and steals the continuation and begins executing it. While it's executing the code, fiber 1 finishes its code and reaches the sink, then sees it can't continue, and is used by some other worker to execute some other code. Meanwhile, fiber 2 reaches the sink, sees it can continue, that there are no outstanding spawns, and it does so. Then something happens in the code that fiber 2 is running, and it resets RSP, specifically to fiber 1's. And then, as we continue running, fiber 2 completely clobbers fiber 1. Now, the reason that we reset RSP is because of what we've been calling the RSP bug. So if you recall, in order to switch from one fiber to another, we set RSP to be the base of the new fiber. Everything then continues on in the new segment of virtual memory. Or at least that's what should happen. But let's look at what actually happens if we try to do that. This is the assembly code as it's generated. So we're in our function, we begin it, we push the base point, save it. Then we move RSP to be the new base pointer. And then we push RBX. I actually don't know if that's part of the calling convention or specific to GCC, but not exactly relevant. Then we change the stack pointer by adding some number to it to get the new stack pointer. Then we do a function. Things happen, we change fibers, and the stack pointer changes. Then when we go to return from the function, problems arise. The way compilers generate the code, rather than retrieving RSP from the current BP value, they just add that same offset back into the stack pointer, which is now pointing to some garbage above the new fiber. Then we pop RBX, and because RSP is garbage, we pop garbage into RBX. Then we pop RBP, and have now popped the garbage base pointer. And then we return, which pops garbage into the instruction pointer. And then we sidefault. This is very hard to attach because GDB will simply say, you sidefaulted on and it lets you, which is really not illuminating. Now, this is obviously not a new problem. It's happened before and it's been solved. So how did the previous runtimes deal with it? Well, Cilk doesn't have fibers, and its manipulation of the stack pointer is much more limited, so it really doesn't deal with it because the same error doesn't happen. Cilk, on the other hand, uses black magic. That's the best way I can describe it. If you look in the source code, it's some trickery involving pointer addition and manipulation and storing it in the full frame, and it's very hard to figure out. I've tried a few times and got confused each time. Now, for Cilk, we thought that we could get around it by resetting RSP to the value before the fiber switch, before the return. The reason we thought that would work is because the Cilk documentation contains a line that imply that the fiber switching use case that causes the bug never happens. It implies that we always end on the same fiber we began on, which obviously isn't true. So, we attempted to port Intel's demonic summoning code to Cilk, and unfortunately we weren't able to. When we tried to, because of some of the differences in how they store the data, everything began to hang. We're pretty sure it's a difference in the locking protocol. So we're getting around this in a new way, and working on yet another minimal runtime called Cilk. And what Cilk is it's purely based on Cilk+. There are no Cilk elements, and in effect what we're doing is we're cutting out all of those non-core features. We're just going in, doing a massive prep, and removing everything that involves them, which is actually very cathartic, I'll note. Now, we hope that Cilk will shed light on how Intel is somehow summoning the outer gods to manage RSP, but we aren't the most confident on that. So instead, if that fails, we'll probably use it as an alternative base for a minimal runtime. So, what does the future hold? Well, we have 3 goals moving forward. First is to finish Cilk, but we haven't given up on Cilk, and failing that, there's hopefully a better way to solve this RSP issue than just copy-pasting the craziness that Intel uses. So, once these tasks have been dealt with, our goal is to load these into a new minimal runtime with a name of either Cilk R, Cilk S, Cilk T, or if I'm feeling particularly arrogant, Cilk K. So, once we have our minimal runtime, our goals going forwards are as follows. Primarily, we want to add those non-core features back in Parlay. So we want to add a nice module reducer implementation. We want to add a nice pedigree implementation. We want to add exception handling, even though almost no one uses it. And most importantly, we want to improve performance, because that's kind of what we do. Here are some further reading, more further reading, and more further reading. Thank you.